Imagine fighting an enemy that's impossible to negotiate with. An enemy that never sleeps, never gets tired, never signs peace treaties, and attacks with the force of an entire ocean. For most countries, water is simply something to defend against. Build a wall, construct a dam, hope it's enough. But one small nation in Northern Europe made a completely different decision. Instead of merely resisting water, they learned how to command it, how to move it, how to imprison it, how to release it with terrifying precision, and eventually, how to turn it into one of the most effective defensive systems ever created. Entire battlefields disappeared beneath rising floods. Enemy armies became trapped in lakes that hadn't existed days before. Ships sailed across land that should never have been underwater, while millions of people continued living safely below sea level. Today, the same engineering philosophy protects airports, cities, farms, ports, and some of the world's most valuable infrastructure. Because in the Netherlands, water isn't just nature, it's infrastructure. It's a machine. And for centuries, it has also been a weapon. When most people hear the word weapon, they imagine tanks, missiles, or advanced military technology. Few would ever think of canals, locks, pumps, or carefully engineered floodplains. Yet these are precisely the systems that repeatedly changed the course of Dutch history. Understanding this story requires ignoring one common misconception. The Netherlands did not become masters of water because they wanted to. They became masters of water because failure meant extinction. Much of the country exists inside one of Europe's most challenging landscapes. Large sections sit at, or below, sea level. Powerful rivers carrying water from Germany, Belgium, France, and Switzerland all converge before reaching the North Sea. At the same time, storm surges from the Atlantic continually push seawater back toward the coast. Fresh water arrives from inland. Salt water attacks from the ocean. Gravity constantly works against everyone living there. The result is one of the most complicated hydraulic environments on Earth. Long before engineers considered using water as a military tool, they first had to answer a far more basic question. How do you keep an entire country from drowning? The answer wouldn't be a single invention. It would become an interconnected engineering system unlike anything humanity had attempted before. And once that system existed, someone realized it could do something no fortress ever could: control an entire landscape. To understand why Dutch engineers eventually weaponized water, we first need to understand the battlefield itself. Because the Netherlands wasn't built on stable ground. It was built inside a constantly moving hydraulic system. Look at a modern elevation map. Something immediately stands out. Large areas appear below the level of the surrounding sea. Some regions sit several meters beneath average sea level. Normally, that would make permanent human settlement almost impossible. Water naturally flows downhill. If your land sits lower than the ocean, nature has already decided where the water wants to go, and it isn't interested in your cities, or your farms, or your roads. Yet more than 17 million people live here today, not because nature allows it, but because engineers never stopped redesigning nature itself. The Dutch landscape is often imagined as flat. In reality, it functions more like an enormous hydraulic machine. Every canal connects to another canal. Every drainage ditch feeds a larger network. Every pumping station communicates with water authorities monitoring levels around the clock. Every lock, every sluice, every embankment, every retention basin forms part of one continuous system. Think of the country less as natural terrain and more as an operating system managing water. One of the most important concepts inside that system is the polder. A polder is not simply reclaimed land. It's land that exists only because engineers continuously keep it dry. Imagine building a shallow bowl. Now place that bowl below the surface of a lake. The moment you stop removing water, the bowl fills. That's essentially how many Dutch landscapes behave. Water constantly seeps inward. Rain falls from above. Groundwater rises from below. Nearby rivers exert pressure from the sides. The sea applies pressure from the coast. Without continuous intervention, the land slowly returns to water. This creates an engineering challenge unlike almost anywhere else. Most countries build flood defenses designed to activate during emergencies. Dutch infrastructure operates every single day, not because disaster is coming, but because disaster is always trying. For centuries, that work relied on an elegant source of energy: wind. The iconic Dutch windmill wasn't originally built because it looked beautiful. It was built because rotating blades could power mechanical pumps. Those pumps transferred water from lower areas into higher canals. From there, gravity carried it toward rivers or the sea whenever conditions allowed. Thousands of windmills working together formed one of history's first large-scale distributed pumping networks. Every mill handled only a small section, but together, they managed entire regions. It was engineering through coordination rather than brute force. Later, steam engines dramatically increased pumping capacity, then diesel, then electric pumping stations capable of moving enormous volumes of water with extraordinary precision. Each technological leap expanded what engineers could control. Larger polders became possible. Deeper land could be reclaimed. Cities expanded into places that had previously been impossible to inhabit. But controlling water wasn't simply about pumps. Timing mattered just as much. Engineers had to understand tides, river discharge, storm surges, seasonal rainfall, groundwater pressure. So they developed increasingly sophisticated systems of gates and sluices. Open them too early, salt water could invade. Open them too late, river flooding might destroy farmland. Close them at the wrong moment. Entire regions could remain underwater for weeks. Managing water became less about strength and more about prediction. Every decision affected another part of the network. Every canal influenced another canal. Every barrier changed water levels somewhere else. Gradually, Dutch engineers stopped thinking of rivers, lakes, and canals as separate features. Instead, they viewed the entire landscape as one connected hydraulic machine. And once you can control an entire landscape, a remarkable possibility appears. If engineers could remove water whenever they wanted, could they also put it back exactly where they wanted? That single question would eventually transform one of the world's greatest flood control systems into one of history's most unusual defensive weapons. Long before satellites, long before radar, and centuries before precision-guided weapons, the Dutch discovered something extraordinary. The strongest fortress wasn't always made of stone. Sometimes, it was made of water. To understand why, we need to look at a simple engineering problem. Imagine an army marching across open countryside. Heavy artillery, supply wagons, thousands of soldiers. Everything depends on predictable terrain. Roads must remain usable. Bridges must stay intact. Fields must support enormous weight. Now imagine changing just one variable. Not enough water to create a lake, but just enough to cover the land. Around 30 to 60 centimeters. To a person, that doesn't sound particularly dangerous. To an army, it's catastrophic. This depth is one of the worst possible conditions for military movement. It's too deep for soldiers to march efficiently, too shallow for boats to navigate. Cannons sink into soft ground. Horse-drawn wagons become trapped in mud. Supply lines collapse. Infantry loses formation. The landscape itself becomes an obstacle. This wasn't accidental. It was engineered. Dutch water engineers understood something most military commanders did not. Depth matters. A meter of water isn't always better than half a meter. Too much water creates a navigable lake. Too little leaves the ground passable. But carefully controlled flooding creates something far more effective: an impassable marsh. Essentially, a giant natural anti-vehicle barrier stretching for kilometers. Creating that barrier required remarkable precision. Engineers first mapped elevation differences across enormous areas. A difference of only a few centimeters could determine whether water spread evenly or simply flowed away. Canals became distribution pipelines. Sluices became control valves. Dikes acted as containment walls. Instead of transporting water through pipes, they transported it across the landscape itself. Every gate served a purpose. Some admitted river water. Others released stored water from canals. Some isolated one flooded section from another. Together, they functioned as an integrated hydraulic control network. The system wasn't designed to flood everything, only selected areas, roads leading towards cities, low agricultural fields, strategic corridors, natural gaps between rivers. Every flooded zone was carefully chosen to force an invading army into predictable routes. Once movement becomes predictable, defense becomes dramatically easier. This was engineering shaping strategy, not the other way around. The remarkable part is that none of this depended on electricity, or computers, or digital sensors. Instead, it relied on information. Local water boards constantly monitored conditions. They understood seasonal river levels, soil saturation, tidal behavior, canal storage capacity, and weather patterns. When danger approached, orders spread rapidly. Workers opened selected sluices, closed others, strengthened weak dikes, directed water exactly where engineers intended. Every action followed predefined hydraulic logic. In many ways, this resembled a modern automated flood management system, except every decision came from experienced engineers, working entirely by observation. The landscape itself became programmable, not through software, but through infrastructure. By the 17th century, Dutch engineers had accumulated centuries of practical hydraulic knowledge. Military planners recognized that this expertise could defend far more than individual towns. It could defend an entire nation. The result became known as the Dutch water line. At first glance, it seems surprisingly simple. A chain of forts connected by controlled flood zones. But beneath that simplicity lay extraordinary engineering complexity. The forts themselves were never intended to stop a full-scale invasion alone. Their real purpose was different. They protected critical hydraulic infrastructure. Think about that. Instead of defending cities directly, soldiers defended sluice gates, canals, locks, and pumping systems. Because whoever controlled the water, controlled the battlefield. The Dutch water line eventually stretched for well over 80 kilometers. It wasn't one continuous wall. Instead, it consisted of hundreds of interconnected engineering elements. Flood basins, canals, diversion channels, embankments, control gates, fortifications, road barriers, observation points. Each component performed a specific hydraulic function. Engineers divided the landscape into compartments. Why? Because controlling one enormous flooded area would have been almost impossible. Smaller sections could be managed independently. If one compartment failed, others remained operational. Modern engineers would recognize this immediately. It's the same principle used in today's flood control systems. Compartmentalization limits failure. Redundancy increases resilience. The Dutch understood this centuries before those terms became standard engineering language. Another challenge involved elevation. Water always follows gravity. So engineers carefully selected areas where flooding could be maintained naturally. Sometimes they reinforced embankments. Sometimes they excavated connecting channels. Sometimes they modified existing drainage systems. The objective wasn't maximum flooding. It was stable flooding. Water had to remain at precisely the right depth. Even small changes mattered. Too dry, the enemy advances. Too wet, boats become possible. Every centimeter counted. That required continuous monitoring, continuous adjustment, continuous maintenance. This wasn't a defensive wall that waited for war. It was living infrastructure, operating every day, maintained every season, improved over generations. And that's what made it so remarkable. The Dutch weren't simply preparing for invasion. They were investing in hydraulic systems that served civilian life, while remaining capable of transforming into national defense infrastructure almost overnight. It was one of history's earliest examples of dual-purpose engineering, infrastructure that strengthened a country's economy during peace and dramatically increased its security during war. But every engineering system has limits. No matter how sophisticated, no matter how carefully designed, eventually, nature always introduces variables that engineers cannot fully control. Ironically, the greatest challenge to the Dutch water line wouldn't come from an enemy. It would come from winter. The Dutch water line was one of the most sophisticated defensive engineering systems ever constructed. But like every engineered system, it had design assumptions. One assumption proved especially dangerous. Water remains liquid for much of the year. That assumption was correct. Flooded fields stopped armies exactly as intended. But Northern Europe has long winters, and during severe cold, the battlefield changed. Slowly, the shallow water that had protected the Netherlands began turning into ice. At first, only a thin layer formed along canal edges. Then entire flood basins froze. Eventually, areas that had been impossible to cross became solid enough for men to walk across. In extreme winters, even horses and light equipment could move over the frozen surface. The very barrier engineers had created risked becoming a highway. This wasn't simply bad luck. It revealed an important engineering principle. Every infrastructure system performs within specific environmental limits, designed for one condition, and another condition may expose an unexpected weakness. The Dutch didn't ignore the problem. They adapted. Soldiers continuously monitored ice thickness. Patrols inspected flooded areas day and night. When freezing began, engineers and defenders acted together. Some sections were deliberately broken open. Water was released beneath existing ice. The moving water weakened its structure. Elsewhere, additional flooding created unstable layers. In certain locations, workers cut channels directly through the ice, not to remove it completely, but to make crossing unpredictable. The objective wasn't perfect prevention. It was uncertainty. An army never wants to advance across a surface that might collapse beneath thousands of soldiers. Engineers understood something psychologists now recognize well. Uncertainty slows decision-making. A commander unsure whether the next kilometer will support artillery must proceed cautiously. And caution buys time. Time for reinforcements. Time for logistics. Time for defense. Again, engineering shaped military strategy. Not through firepower, but through environmental control. The Dutch water line never remained static. Generation after generation, engineers modified it. As surveying techniques improved, flood zones became more precise. As pumping technology advanced, water levels became easier to regulate. As maps improved, weak points became easier to identify. Every conflict became an engineering review. What worked? What failed? What should change? Modern engineers call this iterative design. Build, test, improve, repeat. Centuries before formal engineering management existed, the Dutch were already applying exactly that philosophy. Failures weren't hidden. They became data, and that data continuously improved the system. The water line became less a finished project and more a living engineering experiment. While military planners focused on defense, another revolution was unfolding quietly. Technology. For centuries, windmills had powered much of the Dutch pumping network. They were elegant, renewable, reliable, but they had one unavoidable limitation. No wind, no pumping. Nature still dictated operating conditions. The Industrial Revolution changed everything. Steam engines replaced unpredictable wind with controllable mechanical power. For the first time, engineers could move enormous volumes of water regardless of weather. That single improvement fundamentally changed hydraulic engineering. Pumping stations no longer depended on seasonal wind patterns. Large polders could remain dry more consistently. Flood recovery became faster. Emergency response became more predictable. Steam also expanded scale. Projects that had once taken decades suddenly became achievable within years. Entire lakes could now be drained with unprecedented efficiency. Previously marginal land became productive farmland. Population expanded into areas that earlier generations considered impossible to inhabit. Infrastructure followed. Roads, railways, factories, ports, cities. Every new development relied on one invisible assumption. The pumps would keep working. Later, steam gave way to diesel. Diesel evolved into electric pumping stations. Automation gradually entered the system. Mechanical controls became electrical controls. Electrical controls became computerized controls. Today, many pumping stations communicate continuously with centralized monitoring systems. Sensors measure water levels in real time. Weather forecasts predict incoming rainfall. River discharge models estimate future flow. Storm surge simulations calculate coastal risk hours before waves arrive. Powerful software recommends when gates should close, when pumps should activate, and where excess water should be stored. Yet despite all this technology, the underlying engineering philosophy has barely changed. Observe, predict, control, balance. The same principles that guided medieval water managers now operate through satellites, fiber optic networks, and advanced hydraulic models. The tools evolved. The logic remained remarkably consistent. And that consistency prepared Dutch engineers for something far larger than defending against invading armies. Because by the 20th century, the greatest threat was no longer another nation. It was the sea itself. One catastrophic event would force the Netherlands to build one of the most ambitious hydraulic engineering systems in human history. A project so massive, it would permanently redefine how humanity protects land from water. On the night of January 31st, 1953, the Netherlands faced an enemy no army could stop. A powerful North Sea storm combined with an exceptionally high spring tide. As the storm intensified, the sea level rose higher and higher. Then came the waves. They pounded coastal dikes for hours. Many of those dikes had protected communities for generations. But they had been designed for the storms of the past, not for what was arriving that night. Eventually, the pressure became overwhelming. One section failed, then another, and another. The moment a dike breaches, the physics change completely. Water no longer pushes only against the barrier. It accelerates through the opening. The faster it moves, the more soil it erodes, the wider the breach becomes, which allows even more water to enter. Engineers call this a positive feedback loop. Failure creates conditions that accelerate further failure. Within hours, entire communities disappeared beneath rapidly rising floodwater. Roads vanished. Power failed. Communication collapsed. People climbed onto rooftops to escape. Across the southwestern Netherlands, more than 1,800 people lost their lives. Hundreds of thousands of hectares of farmland were flooded. Thousands of homes were destroyed. The disaster wasn't simply a humanitarian tragedy. It exposed a fundamental engineering reality. The existing system, remarkable as it was, could no longer provide the level of protection a modern nation required. The Netherlands faced a choice: continue repairing yesterday's infrastructure, or redesign the entire relationship between land and sea. The country chose the second option. The solution would become known as the Delta Works. Not a single dam, not one floodgate, but an integrated coastal defense system unlike anything ever attempted. Instead of strengthening every kilometer of coastline, engineers asked a different question. What if we shorten the coastline itself? Imagine protecting a castle. You could build a wall around every building inside. Or you could construct one stronger wall farther out, reducing the total perimeter that must be defended. The Delta Works applied exactly this principle. By closing selected sea inlets, the Netherlands dramatically reduced the total length of vulnerable coastline. Fewer kilometers, stronger defenses, greater reliability. But nothing about the project was simple. Close too many estuaries, and tidal ecosystems collapse. Close too few, and flood risk remains high. Every decision involved balancing hydraulic safety, navigation, freshwater availability, environmental impact, and economic activity. This wasn't merely construction. It was systems engineering on a national scale. Today, the Netherlands no longer thinks about flood protection as isolated structures. It thinks in systems: storm surge barriers, sea dikes, river dikes, canals, retention basins, pumping stations, computer models, weather satellites, real-time sensors. Every component constantly exchanges information with the others. If river discharge increases, reservoir capacity changes. If heavy rainfall is forecast, water levels are lowered before the storm arrives. If tides and river flow peak simultaneously, operators adjust gates across multiple regions. The objective isn't reacting to disasters. It's preventing them before they begin. Modern Dutch engineers even use the phrase, living with water, not defeating it, not eliminating it, managing it, because complete control is an illusion. Water always finds new paths. Sea levels change. Climate changes. Rainfall patterns evolve. Engineering must evolve with them. Ironically, the greatest lesson from centuries of Dutch hydraulic engineering isn't about building bigger walls. It's about building smarter systems. The medieval engineers who first connected canals and sluices, the designers of the Dutch water line, the innovators behind steam-powered pumping stations, and the architects of the Delta Works, were all solving the same problem. How do you control something that can never truly be controlled? Their answer was never absolute resistance. It was continuous adaptation. That philosophy transformed one of Europe's most vulnerable landscapes into one of the safest. It allowed millions of people to live below sea level. It created farmland where open water once existed. It protected some of the world's busiest ports. And for centuries, it turned water itself into a strategic advantage. Not because the Dutch conquered nature, but because they learned something far more powerful. The most effective engineering doesn't fight natural forces. It understands them, predicts them, and works with them. The Netherlands should not exist in the form we know today. Yet it does. Not by accident, not by luck, but because generation after generation of engineers refused to accept the landscape they inherited. Instead, they redesigned it. One canal, one dike, one pump, one floodgate at a time. And in doing so, they transformed humanity's oldest enemy into one of its greatest engineering achievements. If you enjoyed this journey into the engineering that reshaped an entire nation, subscribe to Echoes of Power, because every week we explore the megaprojects, the machines, and the engineering decisions that change civilizations. Thanks for watching, and we'll see you in the next one.